Okay, and let's zoom up. And I better catch the lights real quick, because you can tell, you really can tell now that the light bulb is dying on me, because the color is kind of coming and going. Okay. All right. So let's start with page 428. Let's do an even, because you don't have the answers to those. So let's do number 24. It says a 10 centimeter by 10 centimeter by 10 centimeter wood block with a density of 700 kilograms per meter cubed floats in water. Okay, so we've got, it is a cube that is 10 centimeters by 10 centimeters by 10 centimeters, and it's floating in water. So we got it floating in water. They tell me that the density of the wood is 700 kilograms per cubic meter, and we want to know what is the distance from the top of the block to the water if the water is fresh. Okay, so if here's the water line, what we want to find is this distance right here. What's the height or the water line? So here we go. Density of block is 700 kilograms per meter cubed. So which way do we want to go? Do you guys want to go centimeters to meters or meters to centimeters? Meters to centimeters. Okay. Okay, so when we do that, then the density of water is going to be 1 gram per cubic centimeter. So let's go ahead and figure this one. So we need to multiply by what? Well, kilograms, there are 1,000 grams in one. Oops, I got that upside down. Pardon Miss Wilson, her brain is still left over from the quiz. Let's start over. 700 kilograms, meters cubed. 1 kilogram has 1,000 grams. And then how are we going to handle this meters cubed business? Well, 1 meter is 100 centimeters, but I'm going to have to do that 3 times. Why do I have to do it 3 times? Because meters was cubed. So 1, 2, 3. So I get, for my density of my wood, 700 times 1,000 times 1 times 1 times 1. And on the bottom we have 100 times 100 times 100. So, what now?
I said maybe it would have been easier to go the other way around.
Well, you had to do the same thing either way.
You get big numbers though?
Huh?
You get like
No, the numbers will be a lot smaller.
I don't like writing a lot of zeros.
Yeah, but here's the good news. There's a lot of zeros and most of them cancel out.
Okay.
So this on top becomes a 7 with 1, 2, 3, 4, 5, 6 zeros, and this is a 1 with 1, 2, 3, 4, 5, 6 zeros. Actually, one more zero. So we get the density of the wood is 0.7 grams per centimeter cubed. Yeah. Okay. How do we unconfuse you? Are you okay with the kilograms to the grams piece? And do you know why we're doing that? Okay. We have density of the wood is given in kilograms per cubic meter. But our density, our measurements for our block are in centimeters. So if I find the volume of the block in centimeters, I have centimeters on one side and meters on the other side, and they're not the same unit. So to be able to do this correctly, I need to get all of them in the same distance measure, and that's what I'm doing. So Lawson suggested that we do grams per centimeter cubed since our block is already in centimeters cubed, and then we had to convert. The reason we have to do 3 sets of centimeters and meters is because we have meters to the third power. You have a length you have to fix, you have a width you have to fix, and you have a height you have to fix. So that's why we had to do it 3 times. Is that better? Okay. So, yeah. Okay. Now, here's the quicker way to think about that. The density of water is what in kilograms per cubic meter? 1,000 kilograms per meter cubed. So what I can always do is just to get from here to here, I divide by 1,000, right? So to get from here to here, I should divide by 1,000. And if you remember that, that's a quick way to go. This is the actual math that takes you there. Okay? All right. This one only has 5 zeros. That's what the problem is. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And 7 over 10 is 0.7. So that's how I reduced it. Okay. This one should not have been there. It's an error. Okay. So now we're ready to go. What do we know? If we're trying to find this height, we need to know that density is mass per volume, right? But I want to know how much of the block is above the water line. Does that make sense? And I don't really want to have to do any more calculations if I don't have to. So there should be something like, I don't know, specific gravity that would allow me to know something about percentages inside the water and outside the water because we're working with water. Do you remember what that is? Specific gravity is the density of the object compared to the density of water. So we have our object is 70% of the density of water. So how much of it should be below and how much of it should be above?
30% of it.
30% of it is? 30% is above the water and 70% is below the water. You can always do that. What if they'd asked me something and this had been plastic and oil? Could I still, if it's 70%, if plastic's density is 70% of oil's density, will it still work the same way? Yes. So it doesn't really matter what the two substances are. We call it specific gravity if one of the substances is water. If it's anything else, you just find the percentages. So if Ms. Lopez had cooking oil and motor oil, and she sees that 2/3 of the motor oil goes into the cooking oil, for example, then they have their ratio of densities is 2 to 3. So that works for anything. You only call it specific gravity when you compare it to water. Okay. So what does that mean for us? That means that we don't have to do this. We know 70% of the wood is underwater. So I'm going to take 0.70% of the volume, and we're going to let that be length times width times height. That'll tell us how much is below. 70% of the volume is below the water line. You okay with that? That's the volume below the water line. You find the volume by doing length times width times height. What could you also do? Yeah?
You also just find the total mass of the block
Uh-huh.
using its density and then find 70% of that.
Yep. You could do that. You could also find 30% to find the amount that's outside. Right? This gives you the below water. If you do above water, you would use 30% of the volume, would be the length times the width times the height. And this is actually the one I'm going to do because the question asked me how much of it is out of the water. What's the height out of the water? So I'm going to do the above water piece. So lots of ways to go here. So let's see. 0.30 volumes is 10 times 10 times 10. And our length is 10 and our width is 10, but our height is, I don't know. The whole one is 10 times 10 times 10, but I only need 30% of it is outside. Excuse me. We okay with what I did there? Yes, no? Okay. So then what does that mean that our height needs to be? What is 0.3 times 10? 3. So our height is 3 centimeters. So vertically, 3 centimeters are outside and 7 centimeters are below. Which makes sense because it's 10 by 10 by 10, so 30% should be, the 30% of one of the sides should be what we do. Kind of okay? So let's recap. Let's recap what our thought process was. Our thought process is we got to figure out how much of the cube was outside. What part of the cube height was outside the water? That was what the question was. So the first thing we noticed when we looked at it was, hey, our units don't match. So our first step was fix the units. And then our second step was, okay, we know the density of the new thing compared to water. If we know the density, we also know the percentage that's above and below. Since the block was 70% of water, 70% of the block is inside the water, 30% is outside the water. So then I said, okay, 30% of the volume is outside the water. So what is 30% of the volume? That's what I put on the left side. 30% of the volume is equal to length times width times some amount of height. And whatever amount of height gives me 30% of the cube is the height that I was looking for. So 7 centimeters below water level, 3 centimeters above water level. Okay? All right, let's do another one. Let's see. Yeah, I don't want to do that one. Let me get my other physics book. This one is not in your book, but I'll write what they tell you. Okay, so we want to find what is the tension in the string, and I'm going to draw the picture for you. So, new page. Another buoyant force problem. Okay, so we have a picture that looks like this. We have a string in here. The liquid is ethyl alcohol, which has a density of I have to look it up. Is it? 2,700. Okay, yeah, I just missed that. Okay. Ethyl alcohol is 2,700 kilograms per cubic meter. Is that what it has for the units? And we have aluminum. So here's our, the block is aluminum, which has a density of, I don't know. No, wait, the density of the aluminum is the 2,700. The ethyl alcohol is not given. It's in the book though, so that's the bulk modulus. I don't need that. Ethyl alcohol. Here's the little table. Ugh. Yeah, it'll be less than 2,700. I promise there's a chart in here somewhere that's got those. There it is. Densities of fluids. Ethyl alcohol is 790. 790 kilograms. Aluminum is 2,700, and the volume of the block is 100 centimeters cubed. Okay, so they want us to find the tension in the rope. So we haven't done one of these yet. So the ethyl alcohol has less density than the aluminum, so what would the aluminum have done if it wasn't attached to the rope? It would sink to the bottom, right? So we have gravity pulling us down. We have a buoyant force pushing us up, but the buoyant force would not have won in this situation. The buoyant force would have lost, so we know the buoyant force is small, but it's upward. And there's also a tension force upward. So our free body diagram is going to look like this. Force tension up, and there's going to be force buoyant up. And then there's going to be, so here's my cube, force gravity down. So there's my mental picture, so I know that force tension plus force buoyant minus force gravity needs to equal 0. And then I'm going to change my units to centimeters cubed because that's what I've got for my block. So what did I say the shortcut for that was? Divide all those numbers by 1,000. So this is now 0.79 grams per centimeter cubed, and this is now 2.7 grams per centimeter cubed. That's our quickie math piece. And I'm looking for force tension. So force tension will be force gravity minus force buoyant. And now we're ready to work our problem. So, now that we're ready to work our problem, what steps do I need to take to find the force of gravity? What is force gravity again? How do we calculate that? Force gravity is mass times acceleration due to gravity. To make the numbers easy, we're going to do what? Use 10. Good choice. Okay, so this side is mass times 10. And how do we find the force buoyant? What'd you say, Andrew?
Saying, wouldn't the mass of the block be 275? If you take the volume.
Yep. We got to figure out we got to find the mass of the block, right? So to find the mass of the block, I'm like, oh, I can't do that yet. Find mass of aluminum. So that would be density equals mass per volume. So we multiply by 100 and we get what? We're going to get 270. Sorry, that's a G. Yeah, no, it's my fault. Handwriting bad. Grams. So 270 grams. Oh no, but gravity's in meters per second squared. Okay, I'll worry about that in a second. We'll fix that in a minute. The easiest fix is what? How many kilograms is this? Once again, divide by 1,000. So we get 0.27 kilograms times 10 is my weight, force due to gravity, weight of my block. Now I'm going to stop right there. There was a lot of unit conversions that are happening right now. Have any questions about the unit conversions? Because I wanted to be in the little units because the numbers will be easier to work with and they match what I already had. But when I do that and multiply it times gravity, I can't get to newtons because I don't have kilograms. So I got 270 grams, which would give me 0.270 kilograms. It's another 1,000 thing. All right, now what about buoyant force? What's the buoyant force? It's the density of the fluid, the volume of the fluid, and gravity. So the density of our fluid is 0.79. Our volume of our fluid is 100. And then this is 10 meters per second squared. So we've got a problem here, again with the units. Centimeters, meters. Right? So, it would have been better to go to kilograms and meters. But we'll go ahead and finish this out and then we'll come back and fix it. And cry gently to ourselves. So, force tension, 0.270 times 10 is 2.7 newtons. This piece over here is 0.79 times 100 times 10. So I'm going to move the decimal place 3 places to the right. But I have centimeters squared, sorry, centimeters cubed, and meters per second squared. So I've got a mess on this. Because this one is grams per centimeter cubed. Oh, Miss Wilson. Yay! Look. Centimeters cubed in the density cancels the centimeters cubed in the volume. So all I've really got to mess with is this is grams and meters per second squared. All right, not as bad as we thought. (790) gram meters per second squared, and I'm going to get rid of grams. So 2.7 newtons minus 0.790 newtons would be 1.9091. Calculator. And then we're going to talk about this unit conversion business, because that's what the problem is. 2.7 1.91. Okay. 1.91. 1.91 newtons. Now, it's really easy to get lost in all the unit conversions. All right? We had to do a lot of unit conversions. So let's do this from the beginning. Let's do this from the beginning. Let's change V equals 100 centimeters cubed to meters cubed. Let's just do that at the outset, and then I'm going to work through the problem again. So you might want to just watch this time. 100 centimeters cubed, 100 centimeters, 1 meter, 100 centimeters, 100 centimeters. So centimeters cubed goes, 100 divided by 100 is 1, so I get 1 over 100 times 100 meters cubed, which is 1 over so this is our volume in meters cubed. Let me show you why this makes it easier to deal with. Because it's almost always easier if you get into standard units to start with. Now we do exactly what we did before. Force tension plus force buoyant minus force gravity equals 0. Our block is suspended in the ethyl alcohol. So, force tension, I don't know. Force gravity, force buoyant. Now, I can just fill in everything I have. Up here we had we go back and get the mass over here. So we had 0.27 times 10, and now we just put in the numbers they gave us. 2,700 times 1 over 10,000 times 10. Force tension equals 2.7 minus 0.790. Nope, not 0.790. Density of the fluid. Density of the fluid was not 2,700. Density of the fluid was 790. It helps if you copy the problem correctly. So we get 0.79, 91 newtons. In this scenario, when you go to the standard units to start with, you have a lot fewer unit conversions to deal with. And the problem in this unit is typically not being able to do, it's not the problem per se, it's all the unit conversion that you have to use to get from grams to kilograms or centimeters to cubic centimeters or whatever you're working with. So if you have questions, please feel free to ask. Because that one's easy. It's really easy to get lost when you've got so many unit conversions. Yeah. Why is the what? Because you have, this will help maybe. If I take the meter stick, 1 cubic meter is about 3 squares this way, 3 squares this way, and 3 squares up. Okay? 1 meter by 1 meter by 1 meter. Our box is only this long. You follow that? So our box is this big by that tall. Is that the same as what I showed you with 1 cubic meter? See, each side of the box is 1/10 of a meter. So you don't get 1/10, you get 1/10 this way, 1/10 this way, 1/10 this way. Which is 1/10 times 1/10 times 1/10. Or in this case, the 100s on the first part cancel out, and you just get the 1 times 10,000. Yes or no, or find another way to say it. You have a unit that is meters cubed. It's meters cubed because it's meters this way times meters this way times meters this way. So to change it to centimeters, I have to change the first one to centimeters, the second one to centimeters, and the third one to centimeters. Meters cubed is not a unit. It is a unit that is being cubed. How could I say that another way? What does it mean to have inches squared? What does that really mean? Inches in 2 directions, right? Well, this is volume, so it's in 3 dimensions. And when you multiply them together to cancel each individual one, maybe I'll say this. Let me say it like this. I had 100 centimeters is 1 meter. I multiply it by 100 centimeters cubed. So if I do that, if I only do this once, what do I get? 1 meter on top, but centimeters squared on bottom. I've only canceled one of my x's. It would be just like in algebra class if you had 3x to the 5th times 1 over x. You get 3x to the 4th, not 3. How many x's do I have to cancel out? 5. How many did I cancel out? 1. How many centimeters did I cancel out with this? Just 1. I need to do that 3 times to get all of the centimeters to cancel and change to meters. I think I'll probably just let that sit for now. But it does have to do with the fact that this is a 3-dimensional object. And this distance by this distance by this distance is not nearly 3 feet by 3 feet by 3 feet. It is tremendously smaller. Okay. So, will AP give you that many unit conversions in a problem? Of course not. Right? So what do we want to focus on this problem? Why does the tension have to be bigger than gravity? Or excuse me, less than gravity. Why is tension less than gravity? Because there's a buoyant force. So, let's ask this question. If I was to suck out 75% of the room's air, we would all get stupid woozy. There'd be just a little bit of oxygen. And some of you may know that oxygen deprivation, it can kill you, right? But you also get loopy, usually, before it kills you. So we'd all be kind of goofy. But if we could do that, would we weigh the same, less, or more than we do normally on a bathroom scale? Because we sink in air. So if I stand on a bathroom scale and weigh myself, and then I suck 75% of the air out of the room, do I see the same number or do I see a different number? Why do I see a different number? So there's not as much buoyant force, actually. And you say, well, there's not a buoyant force on you. Yes, there is. It's just wee tiny. And my weight's way big. So my way big weight, wee tiny buoyant force. But if we take the air out, what happens to buoyant force? It goes away because there's no air to displace. So my weight goes up or down. Weight goes up. Because you don't have anything supporting you up. So the downward force would be bigger. Yeah, go ahead, Luke. What were you going to say? And then I'll cover.
I was going to say, also you probably live in since you have like a lot more air.
Yeah. Yeah. And then, excuse me, yes. And so, if we were to weigh on the bottom of a swimming pool, if we were able to do that, what would our weight look like? Greater, same, or less than weighing outside of the water?
Less than 30, not a lot more.
In that case, it would be really noticeable. The difference in your weights out of water versus in water would be really noticeable because the buoyant force on you, the biggest it gets is what? The biggest it gets is your own weight because you float. So force buoyant up and force weight down are exactly the same. So if you were to be able to manage to weigh on a scale at the bottom of the pool, you would weigh tremendously less than you do in air. Okay? Yeah, what were you going to say?
So I was wondering, but like, if there's a pressure add like any weight, like I know the weight, like the air above you can like push you down.
Yes,
kind of, so.
but the air below us also pushes up. So at that bottom layer of air, right down by my feet or the soles of my shoes, that air has more pressure than the air at the top of my head. Because there's more column of air down there than there is column of air to here. And all that air down there has that. So it all pushes up on me. So in essence, the reason you don't feel like your head weighs 8,000 pounds due to air pressure outside is because at every level, the pressures are all balancing each other out left and right, up and down, so that nobody's moving up and nobody's moving down. That's a good question, though. Really good question. Because it's not like, you're standing here and you feel the air particles hit your legs, but they're hitting in the front and the back and the sides and everywhere. So, in essence, all the forces are kind of canceling out. But one of the reasons we do, you may know that when you go scuba diving, they use a pressurized air tank. They used a pressurized air tank to get the pressure inside your lungs to be the same as the pressure outside in the water, or close to it, so that your lungs don't compress and make it very difficult to breathe. That way you can go down further. Of course, there is a limit to that, right? And depending on how far you're diving, they use different rated tanks, different pressures on the tank. And that's one of the things they're looking at doing if we ever go to space. For us to really go to Mars, we need to be able to launch people at a much larger acceleration than is normally capable of handling. Like most people pass out around 4 Gs. Astronauts don't pass out typically until 6 or 7 Gs. Your jet fighter pilots and some of them have to go through those tests to see when you're going to black out. So 4 or 5 Gs is the average untrained human, and your high-end specimens that are doing that are in the 6, 7s. So, but what they're looking at doing is creating a gel that's got oxygen in it, and they would put the gel through your nose and through your mouth so that you would have sort of a liquid all the way through your lungs, which would make you very incompressible, so that you would not feel the accelerations like you would pushing your chest in, compressing you as you take off. And that gel would be, they'd sort of like use tubes like you do at the hospital. Tubes would circulate it, and it would be a mixture that's non-toxic but has oxygen in it, so that when it hits your lung cells, the lung cells can pull the oxygen out, send the other stuff out, and you just keep recycling. That's one of the things they're looking at doing. It kind of sounds gross and scary and nasty to me. And they've talked about if they do that, they'll probably have to sedate the astronauts. because all of us, our reflexes, right, your instincts would be trying to cough that stuff up or pull it out or whatever. So in the movie Interstellar, that's one of the things that's also they're looking at is being able to hibernate people, and they'd be running fluid through your body the whole time instead of actual gas. Still sounds nasty, just saying. Okay. All right, deep breaths from that one. Let's do we want to do one more of these, or do we want to do a hydraulics, or do we want to do a...
Number 26.
Do it number 26?
Well, I'll see if I'm right.
Okay. I can tell you if you're right just a minute.
Oh,
Yes, what was it, Luke?
Hydraulics would be the
Hydraulics one? Okay. Realize the one I gave you on the practice sheet has huge numbers because 17 atmospheres is not messing around. Okay, so hydraulics question. Okay, so let's find one of those in our book. Let's see. Number 34. Masses A and B rest on very light pistons that enclose a fluid. There's no friction. Which of the following is true? Okay, so this is a short answer question, like you might see on multiple choice. So let's draw it and talk about it. We have a thin tube, a big tube. So here's piston A with a box on it. Here's piston B with a box on it. Okay, and it says that the area here is 1 meter cubed and the area here is 2 meters cubed. So which one of these blocks, just to get our brains going back to hydraulics, which one of these blocks would have to weigh more? So the question is, which mass is larger? And I'm going to add the and why. Well, what does hydraulics depend on? It depends on pressure at some particular point. Has to equal pressure at some other point, right? So mass times gravity. This would be force over area. Has to equal mass B, this is mass A, times gravity over 2 meters cubed. So force over area is force over area. The force being the weight of the respective boxes. So which one has to weigh more? The one that's on the bigger platform, because if I want to keep the ratio the same size, I need big number over big number and little number over little number. So in fact, you can look at it like this. This cancels out, and you get 2 times A has to be equal to 1 times B. So block B is the larger mass. Block B would be the larger mass. Now we should do one with numbers on it. see. Here's some more force problems. That's a flow rate problem. Not seeing very many of those in here. Okay, we'll resort to our other book. There we go. Okay, I'm not going to try to draw this. But here's another one. Elephant, 1,200 kilograms. Man, 70 kilograms. Two cubic meters? I don't know. So a man is standing on a platform. 70 kilogram student balances a 1,200 kilogram elephant on the hydraulic lift. What is the diameter of the piston the student is standing on? Well, pressure 1 has to equal pressure 2. They're at the same height. Same height. So force 1, area 1 equals force 2, area 2. And the question asks us for the diameter of this piston. Okay? Not the area, but the diameter. We want the diameter of the piston. So I'm going to start by finding its area, because that's what I can do. So force 1 is 1,200 times gravity, and the area is 2. Force 2 is 70 times gravity, and the area is I don't know. So, cancel gravity. 1,200 A2 equals 140. And no, I can't do that in my head. I get 11.116 repeating. 0.117 meters cubed. Okay. Now how can we find the diameter? Well, actually, let me stop there. Is everybody okay with where all the numbers came from and how they go in? So a hydraulics problem is basically saying force over area equals force over area and solving for the piece you need. How am I going to get to the diameter? What should I do? Yeah.
Divide by pi.
Divide by pi,
And square root
and then take the square, because the area of a circle is pi r squared. So I'm going to come over here and go, okay. Area of a circle is pi r squared. And yes, I'm definitely going to need a calculator for this. Okay, that divided by pi is 0.037. Take the square root. And I get the radius is 0.193 meters. So my diameter is 2 of those. So 0.38 meters, or about 38 centimeters. Okay? Okay, I'm going to stop right here because that's a lot. And then y'all can work some problems and I come back and we